Wireless LAN Measurement Suite contains software for generation and analysis of 802.11a, b, and g signals. In both LabVIEW and CVI, engineers can use the programming API to configure measurement examples. Observe the pellets in LabVIEW on your screen for both generation and analysis. In the background, we can also observe the block diagram of an example configuring an EVM, or error vector magnitude measurement. In fact, the analysis toolkit contains measurements from transmit power to spectral flatness to EVM, or error vector magnitude. In addition, for engineers in the lab, they can also use measurement traces for debug purposes. The common traces given by this toolkit are spectral mask, power versus time, and the constellation plot. The Wireless LAN Toolkit contains examples for both generation and analysis of A, B, and G signals. Here, I'll choose to generate a G signal at 2.412 GHz, a power level of -10 dBm, and a data rate of 54 megabits per second. On the analysis side, I'll perform an error vector magnitude measurement. Using a PXI 5663, I can configure my frequency, power level, and number of averages. When I click on Run, you'll see that the measurement result is better than -45 dB, a value that rivals some of the best-in-class instruments from Agilent and Rohde & Schwarz. In addition to getting started examples, we can also program more sophisticated code to generate a variety of different signal types. Here, I'll choose to generate an 802.11b signal with a data rate of 11 megabits per second. Moving over to my spectrum mask, you can see that I configure the specific mask that will be applied for this signal. In this case, the mask in white is clearly above the red signal, indicating a pass. Of course, I can always observe the constellation and power versus time. 802.11b also contains measurements for both DSS ramp-up time and ramp-down time. Going back to the spectrum, I'll change my signal type and mask to 802.11a or G. In this case, 54 megabits per second is a 64 QAM signal. Here we can observe on the constellation plot that my error vector magnitude is better than -45 dB. On the generation side, we can also change the data rate to something like 6 megabits per second, which produces BPSK. In addition, we can observe QPSK, or 4 QAM, and also 16 QAM. One of the biggest benefits of PXI instrumentation is that many measurements can be performed significantly faster than traditional boxes. In this demonstration, I'll perform 50 EVM, PVT, and spectral mask margin measurements and report the average measurement time for each. On the right-hand side, you'll see my EVM, PVT, and spectral mask graphs update as I perform each measurement. When we look at the results, notice that EVM measurements are performed in just under 40 milliseconds, PVT in just under 25, and spectral mask in just under 50. Now, I can go back and disable the traces for each measurement to make them even faster. When I run again, you won't see the graphs updating, but you will see the measurement times once the measurement is completed. As we can see, the EVM measurement time went from 40 milliseconds to 22 milliseconds. Not only is this a significant time improvement, but it's also significantly faster than many traditional box instruments. Thank you for taking the time to learn about the Wireless LAN Measurement Suite. As we explained, this toolkit allows engineers to use PXI hardware to perform fast, accurate, and flexible RF measurements. For more information, please contact me, David Hall, at 512-683-5661.